Hello everyone, my name is Om and I, along with my group members Sagar, Chod and Shivam, are presenting a project topic as a part of the Graduate Transport Phenomena course in the Department of Chemical Engineering at the University of Florida. Our project focuses on the flow of a species through porous media. The topic covers the concepts of modeling transport of a species across a proton exchange membrane fuel cell. The project focuses on fluid flow modeling, a crucial aspect of transport phenomena, which includes fluid flow, heat transfer, and mass transfer, starting from the Navier-Stokes equation. The Navier-Stokes equation can be divided into five parts for the purpose of explanation. The first part being the local acceleration or the time-dependent term that deals with the change in the flow with respect to time. If the flow is steady state or a fully developed flow, this term goes to zero. The second part is an inertial and convective acceleration term, which deals with the dependence of flow in all the directions. The third term consists of a pressure gradient and must be used if the flow is pressure driven. Further, the fourth term is the gravitational force acting in all the respective directions. And the last term deals with the viscous diffusion that takes place due to the fluid's molecular viscosity. But note that the term V is the kinematic viscosity, a ratio of viscosity and density. Further, the Navier-Stokes equation can be extended into component form along with their required coordinate systems, which are rectangular, cylindrical, and spherical coordinate system. Our topic primarily focuses on the rectangular or Cartesian coordinate system with x, y, and z as the components. The equations of the motions for an incompressible Newtonian fluid flow in rectangular coordinates are as follows. Equation 2, 3, and 4 denotes the equations in x, y, and z directions, respectively. So moving forward, for the modeling of a fluid flow, we need to conserve mass flowing through the fluid flow. To this, we need to introduce the continuity equation that deals with the mass conservation. Equation 5 denotes the continuity equation. For an incompressible flow, the density of a fluid particle is constant along the time, which means that the change in the density across the flow fluid flow length is zero. So this takes us to equation 6 that implies that continuity equation for incompressible flow is delta dot V equals to 0. Further, equation 7 refers to the continuity equation in rectangular coordinate system for the use of this topic. Keep in mind that while an incompressible flow does not always has a constant density, but a flow with constant density is always incompressible. So this topic mainly focuses on flows in porous medias. So materials that have internal pore structures and are solid are called porous medias. Either fluid or nothing can fill the pores. Varying mediums have varying pore structures and sizes. Well, the porous media can be defined in three terms: their porosity, specific surface, and tortuosity. Equation 8, 9, and 10 denotes them respectively. The void volume is the total volume of the void space in a porous medium, while the interface area is the border between solid and the void spaces, while the tortuosity is the ratio of the square of minimum path possible by the fluid to flow with respect to the actual path. Well, all these properties are dependent on the structure of spores and sizes as well. Moving forward, the flow in porous media can be divided into two parts, Darcy law and Brinkman equations. Well, fluid flow in porous media has been studied over a century, with Darcy law first acquainted in 1856. The law states that the flow rate is proportional to the pressure gradient, but is invalid for non-Newtonian fluids and Newtonian fluids and gases at high velocities. It also neglects the friction and momentum exchange between the fluid and solid phase. Well, equation 11 defines the Darcy law equation without consideration of gravity. But if you are considering the gravitational force, you should use the equation 12, which considers the gravitational force in the form of G, where rho is the density of the fluid and G being the acceleration due to gravity. Well, the interspatial space can be thought of an porous media filled with networks or channels. Since the fluid velocity in Darcy's model does not meet the no-slip boundary requirements on the channel wall, the fluid flow in such channels may not be accurately predicted by Darcy's law. That is why we need to rederive the momentum equation for low Reynolds number, which leads us to Brinkman equation, the second part of fluid flows. In these scenarios, the specific permeability of the pore medium is substantially less than the squared characteristic length. Therefore, microscopic changes in fluid velocity must be considered. Equation 13 here refers to Brinkman equation. The further problem statement of our topic will be explained by our group member, Joe.
Before moving towards the problem statement, I'll be giving you an introduction on what a fuel cell is, and I'll also be explaining the working mechanism of a fuel cell. So, a fuel cell is a device that converts the chemical energy from a fuel into electrical energy using an oxidizing agent. I'll be also explaining the key components using this figure over here. So, the first key component is the fuel. Here, in this case, we're using hydrogen as the fuel, but generally the fuel depends on the type of fuel cell being used, and it is introduced at the anode. The next key components are the electrodes, the anode and the cathode. So as you can see, I have the anodic reactions over here and the cathodic reactions as well. So at the anode, the fuel, that is hydrogen, is oxidized, which gives rise to protons and electrons. And at the cathode, oxygen is reduced and combines with the electrons and protons to form water. The fourth key component is the electrolyte. The electrolyte is the medium which allows the transport of ions between the electrodes while preventing the mixing of fuel and oxygen. The fifth key component is the catalyst, which lowers the activation energy, thereby increasing the rate of the anodic and cathodic reactions. The final key component is the gas diffusion layer, or the GDL, which distributes the reactant gases towards the catalyst layers and is electrically conductive. Let's talk about proton exchange membrane fuel cell, or PEMFC. This type of fuel cell uses a solid polymer electrolyte membrane, which is made of PFSA, that is perfluorinated sulfonic acid ionomer. This material only allows protons to pass through it while blocking electrons, and this ensures that the electrons only flow through the external circuit, which generates electricity. I'll be talking about some of the differences between the PEMFC and the traditional fuel cell and what advantages lie with the PEMFC. The first aspect is the electrolyte. A PEMFC, as we just discussed, has a solid polymer membrane as compared to a traditional fuel cell, which could be using liquid or other types of electrolytes. Now, the advantage is that because PMFC does not use a liquid, there is no leakage, and it has a simpler design as well. The next aspect is its operating temperature. The PMFC has a fairly lower operating temperature ranging from 50 to 100 degrees Celsius, whereas the traditional fuel cell has a higher operating temperature. And because of this, the PMFC has a faster startup and is suitable for portable and transportation applications. The next aspect is the type of fuel being used. In the previous slides, we talked about pure hydrogen being used as fuel for the PEMFC, whereas the traditional fuel cell may require reforming complex fuels. And this leads to a cleaner operation for the PEMFC with fewer byproducts. The next aspect is the size and weight. The PEMFC is compact and lightweight. As you can see, the type of fuel being used itself is pure hydrogen. It is the least dense gas being used, and even the components are compact as well. Whereas the traditional fuel cell is often bulky and heavier. And because of this, the PMFC is better for portable and mobile applications. The next aspect is efficiency at low load. The PMFC has a higher efficiency, which makes it suitable for variable power demands. The next aspect is environmental impact. PMFC only produces water and heat, as we talked about before, whereas for a traditional fuel cell, the byproducts vary upon the type of the fuel cell or the fuel. As I mentioned before, the membrane or the PM is made of PFSA, that is perfluorinated sulfonic acid. Now, I have the molecular structure of PFSA on my right side. As you can see, highlighted in orange is the hydrophobic backbone. This hydrophobic group is electrically insulating and hence does not allow free electron movement. Now this group, this ionic group highlighted in blue, is hydrophilic, and this creates a hydrated pathway for protons to move. The third reason is proton conduction. Now, protons get transported through water or a hydrated polymer through a mechanism known as Grott's mechanism. I'll be explaining a bit about this mechanism in the next slide. Now we need to understand how proton transport occurs. Before going to that, we need to note that hydrogen is typically humidified. This is done to ensure that the membrane stays hydrated, as the conductivity of the protons depends on adequate water content. Now let's talk about the proton transport through the membrane. So I have the Grott's mechanism over here, right? As we discussed earlier, the reduction of hydrogen or the fuel produces protons. A proton gets attracted towards a lone pair of electrons on the oxygen atom and binds to it, forming a hydronium ion, so known as H3O plus. Now this H3O plus is also highly unstable and further dissociates to form water and proton. This excess proton jumps to a neighboring water molecule, forming another hydronium ion there. And this chain reaction repeats rapidly, enabling efficient proton movement all the way through the membrane. And upon reaching the other end of the membrane at the cathode region, the protons then react with the oxygen and electrons to form water. So this is the mechanism of how the protons travel from the anode region all the way through the membrane to the cathode region and then react with the oxygen and electrons to form water. So in this problem, we will be discussing the one-dimensional mass transport of oxygen and water in the gas diffusion layer. But before diving into that, let us understand what is the significance and the functions of the gas diffusion layer. So as you can see in this figure, the GDL is a thin sheet that has a porous structure and is made of materials like carbon fiber paper or carbon cloth. The first key function is the even distribution of the reactant gases at the electrodes. The second function is that since it is electrically conductive, it enables electron transfer between the catalyst layer and the bipolar plates. The bipolar plates are missing in this figure, but it is essential to know that the bipolar plates are placed in between the catalyst layer and the electrical circuit. The third function is that it provides structural integrity to the membrane electrode assembly. And the fourth function is that it helps remove excess water from the catalyst layer while maintaining sufficient hydration of the membrane. Now this function is important because the GDL helps mitigate or reduce flooding at the membrane or the catalyst layer while maintaining the sufficient hydration or the water content of the membrane as we discussed earlier. Next, Saga will be describing the assumptions governing equation as well as the initial and boundary conditions for solving the transient model.
In order to describe the mathematical modeling of the system, we consider a one-dimensional cathode GDL model. Here are the assumptions for the same. The catalyst layer is a very thin layer, so we can treat it as a surface where the reactions occur uniformly. The water generated from oxygen reduction is only in the liquid phase. Hence it does not evaporate into the vapor, so any phase change or even movement of water vapor is neglected. We do not consider multi-phase flow for this system, so water is transported through the GDL as a liquid or a single phase. Heat convection due to oxygen gas is neglected since we are assuming that the heat transfer process is very small. The water transport equation is modeled using the continuity equation and a momentum conservation equation. For the continuity equation, we have a transient term which describes how the mass of the water inside the porous medium changes over time, and the divergence term describes the flow of liquid into or out of the region. Epsilon is the GDL porosity, S is the liquid saturation, UL and ρL are liquid velocity and water density respectively. We hold ρL as a constant, so we get a simplified continuity equation. And the momentum conservation is modeled as per Darcy's law, and we have a del PL term which is the pressure driving force for the flow of the liquid, and ρl g cos theta is the gravitational term. Capital K is the absolute permeability, and it depends only on the pore structure and not on any liquid flow properties. KRL being relative permeability is between 0 and 1, and μL is the viscosity of the liquid. Liquid water velocity can be approximated using the capillary diffusion coefficient. In terms of a fuel cell, DC describes how the liquid water formed at the cathode redistributes itself in the GDL. KKRL by mu L can be accounted as one term, which is the mobility of the liquid, and mobility is taken as an order of 1 when we have very high permeability or when we have very low viscosity. The schematic shown is between x equals 0 and x equals LC. At x equals 0, that is the interface of catalyst layer and GDL, we have the following boundary condition. Here there are three terms of consequence, I, F and alpha. Alpha is the net drag coefficient, so it accounts for electroosmotic drag as well as back diffusion. In electroosmotic drag, the water molecules are moved along with the protons between the anode and the cathode, and this occurs due to the influence of the electric field, while back diffusion occurs in the opposite direction as there is a concentration gradient created by water generation at the cathode. I is the current density and it reflects the intensity of the electrochemical reactions. It is a measure of electric current per unit area of the electrode, and F is the Faraday constant which relates the electrochemical reaction rate to the observed current. Coming to the oxygen transport equation, C naught and D naught are molar concentration and diffusion coefficient for oxygen, and the boundary conditions are at the GDL interface, which is at x equals LC. Oxygen transport is critical for maintaining high current density and for efficient operation. This factor of 1 minus 1 by 2 nu air is used to relate the oxygen depletion in the air channel as it is consumed in the reaction. At x equals LC, the boundary condition assumes that there is no liquid water present, which is valid as the interface is exposed to the gas flow and it is free of any liquid water, maximizing the diffusion of oxygen. In both the governing equations, if we put the transient term to 0, we obtain the steady state solutions. Equations 10 and 11 represent this. If we integrate equation 10 twice, we get s of x in terms of dc and two integration constants c1 and c2. On applying the boundary conditions, we get a final equation for s of x, which is the liquid saturation in terms of I, F, alpha and LC as well. From equation 11, we can also obtain a linear equation for the concentration of oxygen, and plugging back s of x, we get c naught of x as this term. Second boundary condition helps define the oxygen diffusion rate at the GDL membrane interface. So as per equation 13, as the water saturation increases, the oxygen concentration decreases. So transport phenomena helps us predict that having more water saturation reduces the cell voltage and thus will lead to reduction in the fuel cell performance. So we need a transient model to define what happens during the startup, shutdown or even load changes. So these dynamics can be used to optimize processes like reducing the startup time, which is required by high performance batteries, minimize the degradation, develop understanding about the fuel cell behavior, like when there is a rapid acceleration or deceleration of electric vehicles. Finally, it is very important for optimizing the fuel consumption and enhancing the efficiency for a sustainable operation.
So as Sagar suggested earlier, developing deeper understanding about the transient behavior of the fuel cell is quite interesting and important. However, due to the challenging nature of the transient models, we need to use numerical models such as finite difference method, finite element method, or finite volume method. Particularly out of these three, finite volume method is quite useful for flow dynamic simulations, where it takes a large system, chunks out into smaller systems, small volumes, enforces conservation laws on top of it, and then solve the partial differential equations. Generally, the workflow of solving species transport using discretization techniques are: first you identify the governing equations, then discretize the geometry, then apply the equations and boundary conditions of the system, then perform the time stepping actions, and then iteratively solve the whole set of equations. But analytically solving coupled governing equations, even with known boundaries and initial conditions, is quite challenging. That is due to the nonlinearity and the variable properties that are involved. Hence, to solve, we have to solve it numerically using finite volume method. So the steps of solving, particularly in this case for oxygen and water transport through PEM fuel cell, are: first, discretize the governing equation for local water transport and oxygen. You can see that this is on the LHS side. This is the time derivative that tracks the local water concentration per unit time, and on the right hand side you have the diffusion of water due to the capillary pressure, and this is the gravity term. Rearranging this, we get the following equation, over which in which the I is the control volume index and N is the time stepping index. And this equation shows how oxygen concentration changes in the porous layers of the fuel cell. On the left hand side, you have time derivative, which shows change in oxygen concentration over time in specific control volume. And on the right hand side, you have the diffusion term, which shows how oxygen is being transported due to diffusivity. Uh, you can also see that water saturation decreases the overall diffusivity and hence negatively affects the oxygen concentration. All right. So next we apply boundary conditions at x equal to 0, that is GDL and membrane interface. And then we use the boundary condition at cathode boundary, that is at x equal to LC. So basically we are going to iteratively solve for S, that is liquid water saturation, and then for oxygen concentration. We use the oxygen concentration that is solved previously to calculate the output cell voltage that is given by this formula. So the output cell voltage actually is a crucial indicator for fuel cell performance, and it depends on the following terms. So E thermo practically means that theoretical voltage that a fuel cell could produce as if there are no losses based on the electrochemical reaction and the cell operating conditions. However, in reality, we do have resistance losses that is created due to resistance of the electrolyte and maybe anode and cathode. Additionally, we also have concentration losses that is due to the reactants being depleted either at cathode or anode. So as we can see that based on these conditions, we can calculate the output cell voltage. This enables us to understand how the output cell voltage would be varying based on our liquid, water, and oxygen transport. This helps us understand how the cell would be modeled, how the performance can be benchmarked, and how can we further optimize it. All right, just like any numerical model, its validation is important to ensure the reliability under real world conditions. So one of the common method to validate fuel cell performance is the polarization curve, which shows the relationship between cell voltage and current density. Basically, it means how much voltage a fuel cell can deliver for the required current load. Okay, let's look at the results. The model was developed using FEM, and that was compared against the experiment data from literature. You can see that the experimental data closely matches with the FEM predicted cell voltage, except for the last 2 points where you have the slight deviation that is attributed to multi-phase effects. Here, only single phase of liquid water was considered. Yeah, this is the table which shows input parameters used for calculation of numerical solution. And finally, we have the power density curve, which shows the how much power can the fuel cell deliver for the required current load. Basically, it is one of the crucial performance indicators of the fuel cell, which decides how much compact it would be and how much efficient it would be. It has power density curve, has real life applications where that gets to decide which fuel cell is getting selected and which is more economical. Okay, let's look at the effect of water saturation and oxygen on the fuel cell performance. As discussed earlier, our model suggests that increasing water saturation negatively affects the fuel cell performance due to decreasing oxygen concentration in the GDL. The first graph shows fuel cell performance with respect to liquid water saturation while keeping the current density constant. You can see that as the liquid saturation increases, the fuel cell performance decreases drastically, and the effect is more pronounced in the lower oxygen concentrations. Moving on to the second graph shows that while keeping the oxygen concentration constant, if we vary the liquid saturation over the JDL, how would it affect? So you can see that with increased liquid saturation, even a slight change in current density, the cathode over potential or the fuel cell performance drastically goes down. This means the water management and gas diffusion layer is very crucial for fuel cell performance. Now let's look at the effect of GDL thickness on the transient behavior of the fuel cell. In this graph, you can see that having a thicker GDL shows that cell voltage decreases drastically over time compared to having a thinner GDL. So hence it makes sense to have a thinner GDL so that our cell voltage should be stable across the time, and that would help us prolong the cell life and have a stable performance. Similarly, in the second graph, you can see that having a thicker GDL leads to having higher liquid water saturation compared to a thinner GDL. And as we established earlier, that higher liquid water saturation means negative impact for the fuel cell performance. Hence, it is obvious that GDL thickness has really critical impacts on the fuel cell performances, and having a thinner GDL would have better water management. So such insights can be drawn from fuel cell modeling, and it helps us optimize and curate fuel cells for specific applications. Just to highlight again, we have assumed unidimensional flow in our fuel cell modeling. However, in reality, fuel cell geometries can be quite complex with 3D flows. Hence, computational tools such as COMSOL, ANSYS help us precisely model the flow while incorporating coupled phenomena such as electrochemistry, heat transfer, mass transfer, etc. It also helps us engineers rapidly test out different configurations to achieve best possible performance in fuel cell while allowing for various operating conditions. So, for example, you can see that this is a COMSOL uh, generated fuel cell PEM fuel cell simulation with oxygen flows on top, oxygen flow profiles on top, and a PEM in between. For additionally, you can also see it COMSOL has been used to model serpentine based field flow patterns, which is like a complex field flow pattern, and calculate the current distribution over the entire thing. So it's evident how useful these computational tools are while modeling this 3D modeling the complex fuel geometries and having even the transient behavior analyzed. To conclude, we can see the central role played by transport phenomena fundamentals in PEM fuel cell design and optimization. Studies such as this to understand impact of parameters such as liquid water saturation, reactant flow rates, and to modeling power density allows us to analyze and improve the crucial processes and mechanisms that govern fuel cell performances. Using these deep insights, engineers can then develop and design advanced materials, optimize operating conditions, find innovative geometries that not only enhances efficiency, reduce cost, and extend durability of fuel cells, but also create pathway for cleaner, sustainable energy systems in near future. Yeah. Thank you.